All right, so when I initially put a wave into the slinky, so this is slow motion. My arm is going back and forth. This was the wave that was going towards Drew. Now, what are some things that we could measure about this wave? Its amplitude, very good. What else? Frequency, what else? Period. What else? Wavelength. Is it moving? And it would have a velocity. So then when Drew started participating and applying a wave in the opposite direction, okay, his is the blue wave. And what you see as the black wave is actually what you were seeing out there. So the result is what you were seeing of the superposition. Back and forth, back and forth. So notice that when they're matching each other, when we've got the red wave and the blue wave on top of each other, we've got a big, huge result. So you couldn't see the red and blue. You were only seeing the result, which is this big guy right here that stretches up and back down. Okay? So all the time, there were waves moving in that string. There was a wave moving to the right and a wave moving to the left. Okay? But what you saw a wave that appeared to be staying in place. We call that a standing wave. Because it appeared to be it didn't appear to be moving. It appeared to be just oscillating in place. So that is a standing wave. All right, so let's define a few of the basic things about a wave before we get too far here. And that's a pretty line there, but here's my wave. And you guys said we could define the amplitude, the height. That's what that little A is right there. All right, so our A stands for amplitude. And what's amplitude measured in? Meters, very good. And you said we could also measure the period. And that would be measured in what unit? Seconds. And you said we could measure the frequency. And frequency would be measured in hertz, right? What else did you say we could measure? The velocity, but also the wavelength. And the symbol for the wavelength is like an upside down Y. It's called a lambda. And wavelength would also be in meters. And then the quantity that we could get from all this stuff would be the velocity or speed. We're going to call it speed because we don't care which way it's going. Meters per second. And we'll use the same little V shape. Okay, so meters per second. How could I get meters per second from any of these fundamental quantities about a wave? All right, so amplitude measures the height of the wave. Wavelength measures the distance the wave travels. So should we use the amplitude or should we use the wavelength? We should use the wavelength. So since speed is meters per second, that would be wavelength. Then I need per second. What's measured in seconds? Period. So wavelength over period. Ooh, what's 1 over period? Frequency. Oh, so that's just like saying frequency times wavelength. So the speed of a wave is equal to the frequency of the wave times its wavelength. That's pretty much a big deal. The one-eye box is good enough. So the speed of the wave in meters per second, the frequency in hertz, and the wavelength in meters. All right, so let's look at our standing wave example. So our standing waves, and the first one is a string. I used a slinky to represent the string because the slinky slides on the floor really well. It also stretches, so it kind of stores some energy, so it actually behaves very well like a string would in that type of demonstration. But we're going to start with the string. Now the most simple wave, the first wave we made in the string, so here was our length of string, and it was either up here, or I'm going to give it an alternate spot, it was down here. So how much of a whole wave, if we use the reference wave of a sine wave over here to the side, how much of a whole wave was in that length of string at any time? Half. So L was equal to half of a wave, half a wavelength. Now let's see. Wavelength is related to speed. So speed of the wave is wavelength times frequency. So wavelength would be 2L. So V would equal 2LF. So if I wanted to find the frequency of our standing wave, I would need to take the speed of that standing wave divided by 2L. So that's the frequency of that first possible wave. The first, I use the word harmonic because it was moving harmonically back and forth with a restoring force and all that kind of stuff. Or sometimes it's called the fundamental. Usually the fundamental is the beginning or the base, so this is the first one, so fundamental kind of makes sense there. Okay, so the second one we could make, number 2. Here was our string, just kidding, and then, didn't it look like this? Whoops, like that, or like that, maybe. Pardon my asymmetrical drawings. So how much of a wave is in this length of string? One whole wave. Okay. I'm going to play the same game I did a minute ago. Speed is equal to frequency times wavelength. So the speed is equal to frequency times L. So our frequency would be speed divided by L. That's a lot of fun, right? Okay, then we made a third one, didn't we? Number 3, we had a length of string, same length of string, same distance. Drew and I did not move our positions. What's happening to the wavelength? It is getting smaller. We're crunching more of our slinky into more wave pieces. So how many waves are in that length of string? 1.5, so 3/2 lambda. All right, I'm going to play the same game again. Ready? So speed is equal to frequency times wavelength. But up here, wasn't our wavelength equal to 2L over 3? So if I make a substitution, speed would be equal to frequency times 2L over 3. Therefore, frequency is what, 3V over 2L? Alright, so let's see if we can notice a pattern. Our first one, and I'm going to put a little 1 right there because it was our first one. Wasn't it V over 2L? And our second one, wasn't it V over L? And this third one was 3V over 2L. Is there any kind of pattern we see? I see V's in all the numerators. I see L's in all the denominators. And I see 2L in 2 of the denominators. How can I make this one match legally? Oh, okay, so 2 over 2. So now they all have 2L in the denominator. They all have V in the numerator. And this is 1, and this is 2, and this is 3. So is there a general equation we could make for the frequency of any harmonic? The nth harmonic would be what? NV over 2L? So that's the money box right there.